doing problems, there are actually a lot of problems that we're going to look at where the acceleration happens to be constant. For example, tossing a ball in the air. The acceleration of gravity is pretty much 9.8 everywhere on or near the Earth. It's 9.8 up to a couple hundred kilometers from the Earth. Now, it varies at the second decimal place, but it rounds to 9.8 regardless of where you are on the Earth. So, it's a great example of when an acceleration would be constant. So there's going to be a number of problems that we'll do that involve a constant acceleration. Turns out we can derive some equations that will work nicely in these situations where we don't have to derive them every single time. We can derive them once and then use the results we get. I'm going to use A to represent our value of acceleration, whatever it happens to be. It could be negative 9.8, it could be 10, it could be 5, but it's going to be constant. It's going to stay the same value the whole time, for the whole problem. So A is going to represent the value of our acceleration. If I know my acceleration, how can I get to my velocity?
Integrate acceleration.
Integrate it. Well, if A is a constant, we can pull it out. We get the integral of dt, which is simply t. But we have to have a plus a constant of integration because we don't have any limits on this. We don't have limits, we have to add the constant of integration. But we can figure out what that constant means. If t equals 0, if I put in 0 for t, that term goes away, so I get v is equal to c. If v equals c, then c has to be some sort of velocity. If t equals 0, then this is going to be the initial, whatever that starting velocity happened to be. We're going to call it v naught. The little 0 will represent our initial value. You can use a little I if you like I for initial. That's fine too. What this means, if we plug this back in for c, what this means is that the velocity at any point in time is equal to the initial velocity value plus the acceleration times time. The nice thing is, this equation right here can be used anytime acceleration is constant. We can always find the instantaneous velocity value if we know the initial velocity value, the acceleration value, and how long it's in place. Now technically this is a vector equation, so we really do need the arrows above it to represent. We need to remind ourselves to put the positive and negative signs on there. So this is fabulous. Very nice equation that we can use in the case of acceleration being constant. But please keep in mind, it only works if acceleration is constant. If your acceleration is not constant, this would not be the result we get when we integrate. You alright with that? If this wasn't constant, we would have a function in there that we were integrating. So this equation is only valid in the situation where acceleration is constant. Now position. Position is the integral of velocity with respect to time. So it's the integral of v naught plus at with respect to time. Well, v naught's a constant. That's just how fast was it going initially and in what direction. So we get v naught times t for the first term. Acceleration's constant. Integral of t is t squared over 2. Again, plus a constant of integration. again looking at it, if t is equal to 0, then x equals c. So that means this constant of integration represents the initial position. Where was your object initially? Now, it could be at its origin, but it may be to the right of the origin, it may be to the left of the origin. We just need to know where it was. So plugging this back in, we get an equation that tells us the position of our object at any point in time. It depends upon the initial position, where it started, depends upon the initial velocity, how fast it was going, and it depends upon the acceleration. It's another fabulous equation that will work as long as acceleration is constant. Acceleration must be constant. It's imperative that you remember that. So this equation will allow us to find the position at any time. That top equation will allow us to find the velocity at any time. So these are instantaneous values. Now it turns out, if you take this top equation and solve for time, and plug it in for time in this equation, then do a whole bunch of algebra, which I'm not going to spend the time doing, the result is this. Now this equation is no longer a vector equation though. You still want to put your positive and negative signs on it. But in the true vector form, it is not written quite appropriately. This equation, though, works nicely because it takes time out of the picture. It relates the velocity and the position directly to each other without time at all. So it's another equation that works nicely. We call these equations the kinematic equations. Kina being the prefix for motion. These are equations of motion. They work as long as acceleration is constant. They do not work if acceleration is not constant.